Hi everyone, in this video we will solve the lead code problem minimum operation to equalize binary string. We are given a binary string s and an integer k, and in one operation we must choose exactly k different indices and flip each 0 to 1 and each 1 to 0. And finally, we have to return the minimum number of operations required to make all the characters in the string equal to 1. And if this is not possible, we have to return -1. Let's break down the idea behind this solution step by step. We are given a binary string and an integer k, and in one operation, we must flip exactly k characters. Ones become zeros and zeros become ones. Our goal is to make the entire string equal to 1, meaning all the characters become 1, using the minimum number of operations. The most important observation here is that the position of the character doesn't matter. What really matters is only one thing: how many zeros exist in the string right now. So instead of thinking in terms of strings, we think in terms of numbers. Let's simplify the problem more and more. So to make this video as short as possible, I have created a written solution so we can go step by step to understand the problem. So imagine that we have a row of light bulbs. Each bulb is either on, which is equivalent to 1, or off, which is equivalent to 0. Our goal is very simple: make all the bulbs on using the smallest number of moves. So what move is mean here? In one move, you are allowed to pick exactly k bulbs, flip them, so the on bulbs become off and the off bulbs become on. And what we really should think about is, instead of looking at which bulb is where, we only care about how many off bulbs do we have right now. So let's say we have 3 off bulbs. This is the current state. So we need to check from 3 off bulbs, can I reach 2 off or 1 off or 0 off, and all the bulbs are on. And if we have 0 off, that means that all the bulbs are on and we reached the final state or the required state. So let's think of it like we have multiple rooms, and each room has a number that represent the number of bulbs. So in room 0, all the bulbs are on. This is the final destination. And in room 1, we have 1 off bulb. Room 2, we have 2 off bulb, and so on and so forth. So each move lets us walk from one to another room by finding the shortest path to room 0, where all the bulbs are on. So how the algorithm should work? First, imagine that we have a queue where we first push the current room or the current state and mark it as visited. Then we try all possible rooms we can move to in one move. This is the next state. And then push these possible rooms to the queue and repeat until we reach the room 0. But how we can calculate the possible rooms? The math should answer this question. If I flip k bulbs as required in the problem description, then let's think about the current state. If I flip k bulbs, how many off bulbs will I have next? When I flip k bulbs, some off bulbs will turn on, while the other on bulbs will turn off. So let's imagine that we have our string looks like 10100 and the k equals to 3. And remember, k is the number of characters that I'm allowed to flip. So if each character of these characters is a bulb, then 1 means on and 0 means off. So we're going to have on, off, on, off, off. The number of the off bulbs here equals 3. And as you remember from previous, if I'm going from room to room, then the current state means that I'll be in room 3 as the number of off bulbs equal 3. As we have agreed that each room shows how many off bulbs we have. 0 all on, room 1 off, and so on and so forth. So again, as the number of off bulbs equal 3, then that means that I am in room 3. So if I am here, my goal or our goal is to go from room 3 to room 0. So remember again that k equals 3. So we must flip exactly 3 bulbs. And we have 3 off bulbs. But how many off bulbs should I flip? Let's imagine that we have a variable x that represents the number of off bulbs that I can pick. So after one move, the number of the number of off bulbs or the new off bulbs will equal the number of the old off bulbs plus k minus 2 multiplied by x. Where these equations come from? Okay, if we flip k off bulbs, then they become on. And as you remember, we are allowed to flip at most 3 bulbs. That is represented by k. So if I flip the x of that k bulbs, then the remaining on bulbs that I can flip will equal to k minus x. Again, if I flip k of bulbs, then I am allowed to flip k minus x on bulbs. So the new of bulbs will equal 3, which are the old of bulbs, minus x. This is the x chosen for the number of bulbs that I'm picking to flip, plus 3, which is represent the k minus x. So if we put all of this together, we're gonna have 3 plus 3 minus 2x. Let's move through the problem step by step using our example of the room. So we start at room 3. So the first case, if x equal 1, and this is the minimum number of zeros to flip. Remember, again, our number equal to 1, 0, 1, 0, 0. So I can choose x to be either 1, 0 or 2 zeros or 3 zeros. So if I started the first case with x equal 1, then I'm flipping 1 off bulb and 2 on bulbs. Then if I applied that to the equation here, the new of bulbs will equal to 4. And this is the maximum flip result after one operation. So that means that I'm moving from room 3 to room 4. The second case, if x equal 2, that means that I'm going to flip 2 off bulbs and 1 on bulb. Again, applying that to the equation. So the new of bulbs will equal to 2. And that means that I'm moving from room 3 to room 2. And the third and final case is that when x equals 3, and this is the maximum number of 0 that I'm allowed to flip in our string. So that means that I choose to flip all the off bulbs and 0 on bulb, and that will give us the number of new off bulbs, which is 0. And this is the minimum flip result after one operation. And that means that I'm moving from room 3 to room 0, which is the requirement because at room 0 we have no off bulbs. So what the algorithm of the code is doing here, first, it tries all the valid x, the different cases here, make sure that numbers stay between 0 and n, because we can't choose something beyond that range. Visit each room once, and that prevents us from being in infinite loop. And to do all of that, we use the breadth first search to get the minimum steps. Now let's move to the original description using the zeros and ones, not the bulbs and rooms. As you see from the above example, we must satisfy two constraints. So imagine if we have variable m that donate the current number of zeros in the string, and this is matched the old of bulbs in the previous example. And in one operation, we can flip k character. So if we choose x zeros to flip, then we can choose k minus x ones to flip. Nothing changed from the previous example. But the value of x should satisfy the following constraints. First, we have to select x to be at most the minimum between m and k zeros. Because let's for example, we have a string that have 5 zeros and k is 3. So at most we can choose just the minimum between the m and k, where m is the whole number of zeros in the string, where k is the number of character that I'm allowed to flip. So at most, I can flip the minimum between m and k zeros. So this can be written as x should be greater than or equal to 0 and less than or equal the minimum between m and k. And also, the number of ones that I can select to pick should be at most n minus m, where n is the total length of the given string, and m is the total number of zeros. So the number of ones that I'm allowed to choose is n minus m. And as you remember from here, we can choose k minus x once to flip. So that means that k minus x should be less than or equal to n minus m. If we combine these two constraints together, we will have this equation that x, which is the number of zero that I can pick, should be greater than or equal the maximum between 0 and k minus n plus m. This is can be deduced from this operation, and x should be less than or equal to the minimum between m and k. So after one operation, the new number of zeros becomes m plus k minus 2x, which is equivalent to, in our example 2, the new of bulbs equal the old of bulbs plus k minus 2 multiplied by x. As I said before, to solve this problem, we will apply the breadth first search. So mainly we are using queues, and each possible value is treated as a node. And also, we will use two ordered set to store the unvisited state separately, one for even and one for odd values. Why we are doing so? Because from a state with even m plus k, we can only go to another state with the same parity. So if you are in a state with even m plus k, that means definitely we can't go to a state with odd n plus k. That is why we are using two different sets. So you will never reach the other parity. For the time's sake, having the code already written here, and let's try to understand it step by step while going through the steps here. So again, I'm having two ordered set to store the states for the even and odd values, and also we have an array distance that record the minimum number of operations required to reach each state. So here we have an array distance. So if, for example, we are in like the example we have seen for the room, if we already in room 3 or started in room 3, that means that that distance at that index will start with 0. And from room 3, as you have seen, we can go to room 4, room 2, and room 0. So when I reach each room of these rooms, I'm gonna increment the distance by 1. So imagine that I'm having an array, and that array is from 0 to 5 to match our example. Then at index 3 is gonna be 0, and at index 4 is going to be 1, and index 2 is going to be 1, and index 0 is going to be 1, because it requires us one step to move from room 0 to either room 4 or 2 or 0. So as you can see here, I'm having this array to store the distance required to move from one state to another or from room to another. And then I'm having a for loop that mainly set or initialize my sets by the even values and odd values within the range from 0 to n. And also it counts how many zeros I'm having within my string s. And for each zero, we are incrementing the variable m to represent how many zeros in the string. First, we need to push the initial number of zero, m, into a queue. So I'm having a queue here. First, I'm gonna push the number of the initial number of zeros in the string, and I'm gonna set the distance of m we have talked before to zeros. And of course, I have to remove the current number of zeros from its corresponding set. The minimum flip result after one operation can be defined by these two equations. How these two equations are calculated here, as you can see, as any normal breadth-first algorithm, I'm gonna loop on the queue as long as it's not empty, and I'm gonna get the first element of the queue, pop it out of the queue, and calculating these two numbers that equivalent to the constraints we have talked before. X1 will represent the minimum number of zeros that we can flip, and X2 will represent the maximum number of zeros that we can flip. Then we will calculate the minimum flip result after one operation and the maximum flip result after one operation. After that, we're gonna select the corresponding ordered set based on the parity of the minimum flip. As you can see here, check if it is even parity or odd parity. And after that, we search the ordered set to find a new element, M2, that satisfies the condition that M2 is greater than and or equal the minimum flip and less than or equal the maximum flip. And for each new element, M2, we set the destination. M2 here means that the new room that we are moving to. So we set its destination to the old, the old distance to the new distance to the old distance plus one. And then we repeat again by adding M2 to the queue and removing it from the ordered set. And so on and so forth. And finally, we'll terminate the process when the queue becomes empty. After performing the breadth first search, if the flipped result 0 can be reached, then we will return the distance of 0. This means if we can reach room 0, then we will return the distance we have so far in destination in distance of 0. Otherwise, we will return -1. And this is all for our explanation for this problem today. Uh, if you like this video, please like and subscribe, and see you in next video. Thank you. Bye.